Hello. So last time, of course, we defined what a homomorphism is, and so naturally the check-in is checking that a couple of things are homomorphisms. So let's get to it. So let's see, each of these is a linear map. This takes the cubic polynomials as input and gives two tall vectors as output. This takes 2 by 2 matrices as input and gives 2 by 2 matrices as outputs. So we'll check each of them. Here we go. So if I have it right, then a plus bx plus cx squared plus dx cubed maps to, it's a plus d, the two tall vector a plus d, and c minus 2a. So, for example, you notice that b doesn't appear, just as an illustration of the kinds of things that can happen or not happen. Okay, so we have to check that it preserves addition and that it preserves multiplication, and we're going to shortcut that by checking that it preserves linear combinations. Okay, so let's see, h of r1 times the first polynomial, so a1 plus b1x plus c1x squared plus d1x cubed, plus r2 times the second polynomial, a2 plus b2x plus c2x squared plus d2x cubed. Okay, so h of a combination. And we've done many of these, so I'm not gonna go through it very slowly. I'm gonna sort of combine a couple of steps. So let's see, h of. So in particular, I'm going to add these two together to get the combination, and it's r1a1 plus r2a2 plus r1b1 plus r2b2 x, and then r1c1 plus r2c2 x squared, and finally see if I can fit in the x cubes. r1d1 plus r2d2 x cubed. I didn't really make it. Okay, so of course now what h does is it takes the constant term and the coefficient of x cubes and puts it on the top of the two tall matrix. Excuse me, two tall vector, and then it takes the coefficient of x squared minus twice the constant term and puts that on the bottom. So we're looking here at r1a1 plus r2a2, that's the constant term, plus r1d1 plus r2d2, and of course that's the coefficient of x cubed, and then on the bottom goes the coefficient of x squared, so that's r1c1 plus r2c2 minus twice r1a1 plus r2a2. Okay, and again, we've done so many of these that I'm not bothering to write where we start and where we need to end. That said, I just assume that a person's done a good number of practice with the isomorphism and remembers what it is that we have to do. So then I'm going to break this into two parts and get what r1a1 plus r1d1, and then r1c1 minus twice r1a1. That was right. And then it's r2a2 plus r2d2 and r2c2 minus twice r2a2. Okay, and then we recognize this as r1 times h of the first, a1 plus b1x plus c1x squared plus d1x cubed, plus r2 times the second, h of, let's see, it's a2 plus b2x plus c2x squared plus d2x cubed. Okay, so we have that h of a combination is the combination of the h's, and that's good enough to show that it's a linear map, that it's a homomorphism. I don't know if I'm going to fit it down. I'm going to give it a try. Okay, so that was question number 1. Question number 2, maybe a little less space this time. So I got to check the G of, and of course I'm taking R1 times the first, A1, B1, C1, D1, plus R2 times the second, A2, B2, C2, D2. And at the end, I've got to get R1 G of the matrix with 1's in the subscript plus R2 G of the matrix with 2's in the subscript. And really, it's the exact same steps. So it's going to be G of, and the matrix is R1A1 plus R2A2. And then R1B1 plus R2B2. And like that. This is R1C1 plus R2C2, and then finally R1D1 plus R2D2. So all I did so far was to add together the combination up here. Of course, exactly what G does is it flips the lower left and the upper right. That's the definition of G. So it takes the upper right and writes it in the lower left. It takes the lower left and writes it in the upper right. Just, I don't know, I had to make something up. I made that up. So that's what G does. So we end up with what here? R1A1 plus R2A2. And over here is R1C1 plus R2C2, just because that's the definition of what G does. And also what G does is to write R1B1 plus R2B2 and R1D1 plus R2D2. So G takes, in its argument, takes the upper right and writes it in the lower left in its output, and then takes what's in the lower left and writes it in the upper right. And then, of course, I'm going to do exactly the same thing here. I'm going to break this up into the subscript 1's and the subscript 2's. So here we go. Need a little more room. I'm falling off of my desk. So we're looking at R1 times, and it's A1C1 B1D1 plus R2 times A2 C2 B2 D2. So it does remind you of this step up here. They're exactly the same in spirit. No, maybe not the algebraic details, but the same idea. And then this, I just recognize this as R1 times G of A1 B1 C1 D1 plus R2 times G of A2 B2 C2 D2. And so the larger view is that I had G of a combination, and down here I got the combination of the G's. So, so the definition of the definition of homomorphism, the definition of linear map, called on me to check those conditions. I combine the conditions just as a matter of convenience, and I find myself, you know, going through the same steps that we went through for isomorphism. Okay. So let's move on then with what it is that we're going to be talking about today. So I doubt you forgot, because it involved is for the homework. But here is the definition of homomorphism: preserves addition, preserves scalar multiplication. Okay. Homomorphism or linear map, either word. I tried to use the one and then the other in turn. Okay. All the stuff that we talked about last time, and it brings us to the theorem that I want to cover today. Theorem says that a homomorphism is determined by its action on a basis. If you tell me what the basis is, and you say what does the first basis element map to, what does the second basis element map to, what does the third basis element map to, etc., all the way out to what does the last basis element map to, and they could be the case that two of them map to the same place. Excuse me. Then there's one and only one homomorphism with that action. There is one. You can't go wrong. If you say to yourself, I want to send beta 1 here, and I want to send beta 2 here, you can't go wrong. Guaranteed there's going to be a homomorphism that does that, and furthermore, that homomorphism is unique. Now, the book has the proof, and so often, as we do in these slides here, because this is an introduction to the part rather than sort of the formal details, I'm trying to give the idea first, and then a person should read it in the book. Okay, so here's the idea. I'm looking to invent a map from the plane to the plane. I fixed a basis for the plane 1, 1, 1, 0. And I'm just arbitrarily sending 1, 1 to 1, 3 and 1, 0 to 2, 0. There's nothing magical about 1, 3. I don't have to meet any conditions on 1, 3. I can do whatever I like with 1, 3. That's whatever I like is perfectly fine. The point is that if you tell me where do these two basis vectors go, if you tell me what is the action of h on these two basis vectors, then I can figure out the action of h on any other member of the domain. So I picked a member of the domain minus 1, 5. I didn't pick it for any good reason. I just made it up as the first one that occurred to me. First thing I do is express minus 1, 5 as a combination of basis vectors. That is to say, I represent minus 1, 5 with respect to the given basis. The given basis here is 1, 1, 1, 0. Represent minus 1, 5 with respect to that basis. It turns out when you do the Gauss's method arithmetic, or maybe you're good at this and can see the answer, it turns out that it's 5 times the first minus 6 times the second. And now I just use the definition of homomorphism to compute where does h map minus 1, 5. So here we go. H of v is minus 1, 5. The definition of homomorphism says you can expand the minus 1, 5 as a combination of basis vectors, so I did. And then I know that this will be 5 times h of 1, 1 minus 6 times h of 1, 0. So to get from here to here, this is 5 times h of 1, 1. You'll remember h of 1, 1, there it is. Minus 6 times h of 1, 0. And there's h of 1, 0. And then just do the arithmetic, you get minus 715. Oh, I got minus 715. Whether it's the right answer is another matter. Okay? So if you tell me where h sends a basis, I can tell you where h sends anything. More sort of slickly said, homomorphism is determined by its action on a basis. Another example. I'm going to find a map that sends R3 to R3 by telling you what it does to the standard basis. That's 1, 0, 0, that's 0, 1, 0, that's 0, 0, 1. F sends 1, 0, 0 to this vector, F sends 0, 1, 0 to itself, F sends 0, 0, 1 to this vector. Okay, so we saw on the last slide there are two steps. Figure out, if you want to figure out the effect of f on some member of the domain, and I just picked minus 5, 0, 10, I don't know, I just made it up. A lot of times when you do these, it's better to do a generic one rather than say 0, 0, 0, or so. It's better to do kind of a made up screwy numbers one. It illustrates the point better, so that's what I did. I made up minus 5 and 0 and 10 just because it has relatively screwy numbers. So, the last slide we saw that the idea is to represent that vector with respect to the basis, but there's no, oops, I have one too many E3s here. I'm sorry, that's a typo. But there's no, there's no difficulty with representing with respect to the standard basis, because we know that with respect to the standard basis, a vector is represented by itself, so I saved myself a little arithmetic on this line. By using the standard basis, I saved myself a little arithmetic at this stage. And then to figure out what does f do to that generic vector, that vector that I just made up some crazy numbers, well, you simply write minus 5 times f of e1, 0 times f of e2, 10 times f of e3, and you do the arithmetic and it comes out to that. Okay, so again, the function f is determined by its action on a basis, by its effect on a basis. If you know f of e1, f of e2, and f of e3, then you can figure out what is f of anything at all. This idea of you figure out where f sends an arbitrary thing by taking the minus 5, the 0, and the 10, and multiplying it by the three vectors that we saw in the top line. That has a terminology for that we'll be using. So v and w are vector spaces, b is a basis for v. A function defined on that basis. So if you tell me where does f send e1, where does f send e2, where does f send e3, a function defined on that basis can be extended linearly to a function that's defined on all of v. So here f maps b to w, here f hat maps v to w. In the way that that example illustrates is that if you tell me that v has coefficients of c1 through cn, then the action of the map is that f hat of v has coefficients c1 through cn, and that's it. So that's called extending linearly. So you tell me how to define the action of the map on the basis, and I extend linearly to the entire space to get the action of the map on any element of the space. You figure out what are the coefficients, and you put those coefficients down. Here's an example to try to illustrate that this is, try to illustrate just how useful this is. So here's an example. I'm going to figure out the formula for rotating in the plane. So here's the action t sub theta that rotates vectors in the plane through an angle counterclockwise of theta. And these drawings obviously show that the map satisfies addition and scalar multiplication, so it's a linear map, it's a homomorphism. I happen to have illustrated with pi over 6, but there's nothing magical about pi over 6. Okay, and here's the formula. This extending linearly idea gives you the formula for this very easily. And the formula is simply this. Fix a basis for the domain, and I'll fix the standard basis, because as we saw a couple slides ago, it saves you a bit of arithmetic. Figure out where do the basis vectors map under the geometric action that you want. So the geometric action is to rotate by theta radians counterclockwise. So 1, 0, there's 1, 0 in gray, rotated counterclockwise gives you cosine theta sine theta. 0, 1, there's 0, 1, there's 0, 1 right there. There's 0, 1, rotated counterclockwise by theta, radians, I suppose you could do degrees if you were insistent, gives you that for an endpoint of that vector, minus, it's clearly negative, right? The x component is clearly negative, minus sine cosine. So you figure out where the geometry tells you the basis goes, and you just extend linearly. To figure out what happens to an arbitrary x comma y, a general x comma y, expand x comma y in terms of the basis, the vector xy, expand it in terms of the basis, apply the definition of homomorphism here, that homomorphism of a combination is the combination of the homomorphisms. T of theta of 1, 0, it says right here. T sub theta of 0, 1 says right here. You get this, that's this. So this is the formula for rotation of x comma y's in the plane. And I got it simply by specifying where does the geometry tell you these basis vectors go. Once you know where the basis vectors go, it's just a question of writing down working through the details of homomorphism. The formula drops right out. Here's another example, illustrates the same thing. This theorem is extremely handy. This idea of extending linearly is extremely handy. So one basis for the space of quadratic polynomials is x squared comma x comma 1. In some ways, it's the most natural basis. So I'm going to define a map, eval sub 3, by specifying where it sends members of that basis. It sends x squared to 9. That's a member of R1. This is the one-dimensional real space. It sends x to 3, and it sends 1 to 1. And of course, as sort of thinking people, we say to ourselves, well, the 9, the 3, and the 1 were chosen because if you were to plug in 3, you'd get 9. If you were to plug in 3, you'd get 3. And if you plug in 3, you'd get 1. But the linear algebra doesn't care about your motivation for sending x squared to 9, x to 3, and 1 to 1. The linear algebra works the same no matter what you did. So I just extend linearly that eval sub 3 on any quadratic polynomial gives you 9a plus 3b plus c. For instance, eval 3 on x squared plus 2x plus 3 gives you 18. So evaluation, what you might call in calculus plugging in, evaluation is a linear map. Evaluation by plugging in 3 is a linear map. Okay? A special case, just like a special case of isomorphisms was automorphism, so too a special case of linear maps is when you look at a linear map from a space to itself. I'm going to use the terminology, this is not standard terminology, but I'm going to use the terminology linear transformation. So many authors, most typically authors, use linear transformation as a synonym for a linear map, as a synonym for homomorphism. I'm going to restrict myself. I'll only use the word transformation when I'm talking about the same domain as codomain. I don't know, I like it better since I think of the space as being transformed in some way by the map. But anyway, just a heads up, if you look on the internet or in another book, they'll use the term transformation to mean in general any map. But I'm going to stick for those maps that send a space to itself. And obviously the identity map is a transformation. To check that it's linear is really trivial. I won't bother you with it. Here's another example of a linear transformation. I'm going to reflect vectors over the xy plane. So you know, sort of close your eyes and think of the think of the yz plane. I misspoke. I said xy. Think of the yz plane. So I think of that as kind of being the right wall. So you think of the yz plane and you have a vector out in space and you reflect it across the yz plane. So in general, if you have, for example, 5, 4, 3, it maps when you reflect it across the yz plane to minus 5, 4, 3. If you had negative 6, 1, 2, that would reflect to 6, 1, 2. And checking that it's a linear transformation, checking that it's a linear map is perfectly routine. I'm restricting the term transformation to those cases where the space maps to itself, so clearly that applies here. And then checking that it's a linear map is very straightforward. F sub yz of a combination is a combination of the f sub yz's. Okay. And then I want to finish today by observing something about linear transformations, about linear functions from V to W. So if you look at the vector spaces V and W, then the set of linear functions from V to W, that's a set. You have a whole bunch of different linear functions from V to W. I'm observing something about that. That set is in fact itself a vector space. So I got to tell you what's in it. Well, I actually already told you what's in it. It's a collection of linear functions from V to W, and then I also got to tell you what is the addition operation and what is the scalar multiplication operation. So as usual here, I'm going to do some examples instead of going through the sort of letters version of this. I'm doing examples, and the letters version is in the book, but I'm using a script L there to denote the space of linear maps from V to W. So what do I mean by adding two linear maps? What do I mean by scalar multiplying? And well, we actually know. So suppose I look, for example, at two linear maps from the linear polynomials to the plane. And maybe here's this first map that takes in linear polynomials and puts out two tall vectors, and here's a second map that takes in linear polynomials and puts out two tall vectors. And it's easy to check that those are both of them homomorphisms, linear maps. And what does it mean to take a combination of them? Well, we know what it means to take a combination of them. 2 times the first plus 3 times the second on the input. So 2 times the first plus 3 times the second should be, you take 2a0 plus 2a1 and add it to 4a1. And so I think you get, 2a0 plus 2a1 and add it to 3 times 4a1. So that's 12 and 12 and 2 makes the 14, and the a naughts is 2. That's right, that was right. And then I'm taking 2f plus 3g on the second component. So 2 times 0 plus 3 times a1 does give you a1. So I did the arithmetic right. So we know how to add two such functions, and we know how to scale and multiply such functions. So we already know what is the algebraic operation that takes place here. How do you add two of these folks, two functions from V to W, and how do you, two linear functions from V to W, and how do you scale and multiply? We already know. So this is a place, this collection of functions from V to W is a place where linear combinations can take place. if you take a combination like 2f plus 3g, that will still be a linear function. Now, of course, I have to check that with a's and b's and i's and j's, but it sure looks like it's a linear function. Okay, it's closed under linear combinations. Another example. So I'm going to look at the linear maps from R to R2. And a member of script L of R to R2 is a linear map, and a linear map is determined by its action on a basis. So I'm going to fix bases. I fixed sort of the canonical basis for the one-dimensional space and the canonical basis for the two-dimensional space, the plane. And so functions are determined by basically where does this basis element 1 get mapped to? So you have to figure out what's the coefficient of 1, 0 and what's the coefficient of 0, 1. And so we can understand what it means to be a member of this space. It just depends on what is your C1 and your C2. So I could write each member of the space as H sub C1 comma C2. That's two parameters, and so in fact the set of linear maps from R to R2 is a dimension 2 vector space. Perfectly fair vector space, it's got dimension 2. Okay. Okay, that ends it for the day, and when we come back, we're going to talk about an important factor of these spaces, of what is the range and what is the null space. Okay, very good. Bye-bye.